this problem is basically using the dynamometer curve. You can assess the how much force, maximum force, minimum force, counterbalance force, all these things you can calculate. So the D max, if you have a curve, let's say ideally the curves will be like completely this one or maybe some small, but when you get surface curve means actual dynamometer curve, the curve will not be like completely rectangular or completely straight line will not be there. So initially the curve may be like this, it will go like this, it will go like this, because it is a combination of many things. Okay, so this may be your curve. So this area under this one shows how much force is you need in the in the motor or IC engine, so that your system will be running. So here some parameters are given. D minimum is 0.63 inch, D maximum 1.2 inch, and L is 2.97 inch. Okay, and area A1 is here, A2 is here, area is given 2.1 inch square and 1.14 inch square, L is given 2.97 inch, and calibration constant is required because you want smaller curve or bigger curve. Based on that, if you want to calculate, then there will be problem. So you have to know the calibration constant also. So pump company or dynamometer, those manufacturing companies, they should give the calibration constant. So here one constant is given 2800 pound per inch, and stroke length is given 45 inch, and speed SPM is 18.5. So they are asking to calculate maximum load. So there is some basic formula. So formula is of maximum load is C into D1. Max load equals C D1, and mean load formula equals C D2. Okay, so you see D mean, so just multiply with C, you will get minimum and maximum load. Okay, range of load equals C D1 minus D2. Upstroke load is C into A1 plus A2 divided by L. This is average. So average downstroke load equals C into D3, C into D3. Okay, so actual counterbalance load, equals half into average upstroke load, plus average downstroke load. So polished rod horsepower, polished rod horsepower will be coming as CA2 by L into SN 33000 into 12. Okay, length is the length of the card, S is the stroke length, SPM. Okay, now the calculation is the max load CD1 equals 12,800 into 1.2 equals 14500 pound. Minimum load equals CD1 or D max, D mean, 12,800 into 0.63 equals 8100 LB. Range is range not required now. Average upstroke load is equals 14800 if you put all the values A1 A2, then you can get 14800, and average downstroke load you can get A1 by L3, C A1 by L3. Okay, so this is giving 9100 pound. Okay, so correct counterbalance mass, correct counterbalance equals C into A1 plus A2 by 2 by L equals 11500 pound. So HP polish rod, PRHP, I can say PRHP, polish rod HP horsepower equals it is coming 10.3. Okay, so this is the calculation. So student, please try to solve this similar problem so that you can solve this assignment problems. Here is another problem. Maximum minimum load of a pumping installation were determined from a dynamometer cut to be 15 diameter cut to 15,500 and 3,500 pound respectively. The well has 2-inch plunger, 7-8 inch rod with tubing anchor set 5,000 feet. Counterweight on the counterweight is given 6,000. Counterweight on the unit weight is this one. The unit dimension is given 40 inch. Okay, so that one first I have to draw one picture actually. Now let's draw the picture. This is my walking beam. Okay, this is CW counterweight, counterbalance effect. Okay, this is saddle point. Here the Samson post will be there, and this is O, this is R, this is L1, this is L2, this is L1, this is L2, and FP pumping force, buoyant force, and counterweight WC, counterweight. Saddle bearing. Okay, so total counterbalance effect, CT equals CS plus CW. So counterbalance effect and approximate structural balance, CS structural balance, approx structural balance. So and CW equals WC D by R L1 by L2. CW CT equals CS. This formula you have to remember, D by R into L1 by L2. Okay, so using that you have to solve the problem. So here you have to get CS and CT. Okay, so now you apply the formula, CT equals CS WC D by R plus L1 by L2. L1 by L2, L1 equals L2 given in the problem. Now CS equals from this equation actually it will come like this, CT minus WC D by R, L1 by L2 not plus this multiplication. Okay, L1 L2 equal, so this is 1 ratio. Okay, So finally it is coming like this: 10,000 given CT value minus 6,000 given, and D value also given 40 and 28, this value R value also given. So CT becoming max load plus mean load divided by 2. So finally 15,500 plus 35,500 by 2 equals 9500 pound. Okay, this is the answer. So ideal counterbalance effect. Okay, so here is another problem. It is again taken from Kermit Brown book. So pumping system has following: buoyant weight of the rod W2 10,000 pound. Buoyant weight means you are putting rod into water. Actually, when you are pumping rod inside water, so it is having buoyancy effect. Okay, so buoyant weight is given 10,000 pound and fluid weight also given 4,000. So counterbalance you calculate. So counterbalance, so CB you can write. Okay, counterbalance you are calculating WF by 2 plus W2. Okay, fluid load plus your buoyancy rod load. So fluid, how much weight is there and how much relative rod weight is there. So that one you are calculating. So 4,000 divided by 2 plus 10,000. So you are getting 12,000. Okay, unbalanced force. Unbalanced force unbalanced force during upstroke equals upstroke load minus counterbalance. Okay, so you are getting 10,000 minus 4,000, 10,000 minus 4,000 minus 12,000, so 2,000. Okay, now downstroke you are getting unbalanced force equals 12,000 minus 10,000 equals 2,000. So upstroke downstroke unbalanced force both are same. So whenever you are calculating unbalanced force in counterbalance, actually that much of force will be given by motor. So that one you have to calculate from fluid weight and rod weight. Okay, one more problem: calculate piston displacement, or how much fluid is getting delivered by pump, and speed SPM also you have to calculate, and given volumetric flow rate 70%, oil flow rate 166 barrel per day, pump intake set as 5050, plunger is 1.5, specific gravity fluid is given, tubing outer diameter also given. So tubing inner diameter actually you have to guess. So EV equals Q of flow rate by V. So from here you can get V equals PD, so equals Q by EV 166 divided by 0.7, 70%. So you are getting 237 barrel per day. So small bd, capital BD, I think there should be some unified unit, otherwise everyone is using different notations. API table, if you see API table, if you do not have access of API table, normally I'll give the value in the problem itself. So PD, there will be several tables if you see the books, and you have to find several parameters, but with this online course you cannot give all the tables. So if you require, I will give some value, or maybe I will give the specific table so that you can take data from the table. PD equals 0.1166 SP NDP square, diameter pump plunger square. This will give 0.09328 SND square. So from there you are getting SNDP square equals PD, the actual suffix, PD 0.09328 it gives 237 0.09238 9328. So 2541. So Sn equals 2541 dp square equals 1130. dp is given equals 1.15 inch. Here in this problem, tubing outer diameter is given. Assume SP by S equals 0.8. okay, because if I do not give, then again there will be difficulty of finding tables. So I should when I'll be giving problem for exam, normally I'll give this condition also. SP equals 0.8 by S is assume 64 inch. Okay, so then N you get 17.7 SPM. okay, and if you have tubing stretch, then curve becomes little bit slanted. All right, but ideally what happens? Ideally means actually when you measure on the polished rod area, so this is your actual curve, pump curd. okay, so when you are lifting up your plunger, so there will be certain extension of rod and stick, some other parameter will be changing. So initial when standing valve is opening, so that time you need some extra pressure to break this static condition of standing valve, and you have to cross some other friction and other things. So you need initially very high pressure, it will go down, again it will go up. okay, then again you are going down, again it will go up like this. So your ideal curve will be maybe complete rectangular, completely straight line, but actually it is not happening like this. okay, so TV closes, standing valve opens, TV opens, SV closes. So ideally if you have very slow speed, then maybe you can resemble the rectangular shape, but if you have higher speed, then actually you cannot resemble, so your shape will change. okay, and you got surface dynamometer card and you got this type of card. okay, now I want to ask you, draw pump curve. So there are several wave equations. So that wave equations, actually it will eliminate this rod motion and other motions, and it will give only the pump area dimension. So in that case, what will they do? The wave equation will be removing all this unnecessary part, and it will make like smooth curve. okay, so that will give your pump curve. So there will be two curve, one will be surface dynamic curve, one will be pump curve. okay, so pump curve does not show rod motion. okay, but surface dynamometer curve surface diameter curve, it shows all. Okay, why this diameter curve is required? Actually, diameter curve if you have, then you can understand whether your pump filage is there or not, tubing is having any problem there or not. So many parameters or properties of wellbore and your pumping system you can understand from this dynamometer curve. And if you approximate through your wave equations, I can eliminate this tubing and rod effect, then you can get idealized one curve. So to understand the whole pumping system, you have to understand the dynamometer curve and pump curve, so that you can understand your wellbore and your pumping system performance also. Now next thing is that now you got certain pump with very high gas. okay, initially gas was very low, but later you got gas. What will happen? So if you have very high amount of gas, in that case you have to use on pump off controller. Pump off controller, what does it do? Pump off controller. So pump off controller, the task is that it will stop pump or use VFD. Okay, you have very low amount of liquid coming, let's say 10 barrel per day, and you are trying to pump 20 barrel per day. So that means there is some gap in between supply and delivery, right? So demand and supply. Then what happens if you have demand high and supply low? So in that case, gas will be formed in the cylinder. Okay, now gas is getting formed and you cannot manage. So in that case, what you do, you switch off the pump for a certain period, allow liquid to accumulate, liquid column to build up, then you pump. Again you stop for a certain time, again you pump. So that you can do. Another way is that you run the pump continuously but change the speed. How to change the speed? Change V belt, change gear? No. These days we have variable frequency drive. Variable frequency drive, it will change electrical frequency. That frequency will change your motor speed. When motor speed change, your whole SPM, stroke per minute, will change. Per minute, maybe out of initially you were pumping 10, now you make it 5. Very slow speed. So slow speed means you are reducing your flow rate, liquid flow rate. So you give enough time liquid column to build up from the reservoir to wellbore, then you pump. Okay, so these two options are there for you for if you have gas accumulation inside cylinder. Okay, so there are two issues. That one issue is that very low fluid coming. Another thing is that you are creating two-phase flow actually. When fluid entering your pumping area, so that time you are reducing pressure. Okay, when plunger is moving up, cylinder, you are reducing pressure. Reducing pressure means if there is any dissolved gas, it can go out. Okay, if it is creating two-phase flow, you can get gas. So it is not like water flow on the surface. Water flow on the surface means we are assuming there is no gas actually, small amount of gas that we can handle. But wellbore actually, it is, if it is creating two-phase flow, or if we have already two-phase reservoir, then you are getting gas and liquid, then life will be different. So in that case, you have to use maybe gas anchoring system. Okay, put your pump below your perforations, or use some pour boy gas separator or casing gas separator, or you use gas lock breaker, or you use this pump of controller mechanism. Okay, so we'll go to next rod system. Okay, one more topic is there. If fluid load on pump. Fluid load on pump. Okay, if you draw dynamometer curve, normally we say fluid load. So fluid load on pump is when you are lifting fluid, how much load it will give. So this formula is there. FO equals AP del P equals pi by 4 dP or plunger diameter square P dP minus PIP. So I use different term actually. Okay, so this is PIP, pump intake pressure. Pump intake pressure. Intake pressure. And FDP actually, PDP is pressure at delivery side. Okay, I use tubing pressure, P tubing I wrote in previous case. So this is actually delivery pressure, pump delivery pressure. Okay, DP is diameter of the plunger, plunger diameter, plunger diameter, P, DP. Someone write capital B, that is also fine, but you have to use uniformly whatever unit symbols you are using everywhere. Okay, so PIP equals CP 1 plus HDFL by 40,000. This unit conversion thing is the pump constant. CP is pump constant, and HD dead fluid load gas free. This is dead fluid load. Okay, and PDP. Okay, so this difference PIP okay, this difference is del P. PDP and PIP, this difference is del P actually. So PDP equals tubing pressure plus 0.433 into SG oil into HSN. PIP, no, PIP some more term is there, plus 0.433 SG oil into GFLAP. So it is okay, I have to draw the picture actually, G flap. Okay, so I'll draw one picture. This is your casing, this is your tubing, this is your barrel, okay, and this is your plunger. Okay, now PIP is here and PDP, right, PDP is here, or P wellbore I said, P tubing I said, there was I use different term there, but here del P I have seen there, del P. Okay, and if we are assuming gas is like this, okay, so up to certain level gas and water liquid mixture will be there. After that gas will not be there, only liquid column will be there. Okay, so G flap is showing that actually gas area, how much area is having gas. Okay, so that area G flap, and HSN is equals to true vertical depth, true vertical depth, they are showing HSN, and PDP G flap, this one. Okay, now tubing stretch, TCH, tubing stretch formula equals K tubing into L tubing into F pull. Okay, tubing constant, tubing length, okay, tubing spring constant, tubing length, and F pull actually how much force you are applying. So that would be giving total tubing stretch, how much elongation is happening because of tubing pulling load or force. Total downhole plunge, total downhole plunger stroke length, S equals SL minus stretch rod plus over travel. Okay, SL is a stroke length. Okay, S is the rod stretch. And over travel. So in that way you can get plunger stroke, actual plunger stroke actually.